Buffer overflows are one of the oldest computer vulnerabilities. However, despite them being well known and exploited for 40 plus years, they still account for a significant portion of 0 days found in modern day software. To help teach about and demystify the buffer overflow, I've created Overflowme, a binary and walkthrough to help teach about the basics of stack and buffer overflows. In this video, I'm going to be walking through the first level of it. I'll show you every step along the way and provide downloads for all of the binaries and documentation so you can follow along. Let's hop over to the computer and get started. If you want to follow along yourself, all of the source code, instructions for building the binary, and the details for the walkthrough itself are included in this GitHub repo, which I will link down below in the video description. Before you kick things off, make sure to read through the general README, and in particular take a look at the Getting Started section and make sure that you have all of the required tools and prerequisites installed. And then once you've got all those, head down to here, grab the URL for the repo itself and clone it, and then you'll be ready to follow along with me. Inside of the repository is directories for each level, and inside of each directory is a README that gives the challenge details and the walkthrough for that specific level. So for Overflowme level 1, the basics, your challenge, should you accept it, is to get the Overflowme binary to print out the hidden message, "Hey, you're not supposed to be here," without modifying the source code. So for all of the levels, if you want to follow along with the walkthrough, then you can just scroll through the README and it will give you detailed instructions, including all of the commands to run that you can just copy and paste. And it has a lot of extra added details for learning as well. So for us, the first step is just going to be to assemble and link the assembly source code, and we can do that with a make file that's provided. So we'll just go make Overflowme, and then we can just simply run it with /overflowme. We get this message, "My buffer is open for input, please don't overflow me." And it's asking for an input here from the keyboard, so I'll just put in a test here. I'm going to say hi from Andrew. Hit enter, and then all it does is just echo it back to us and say thanks for not overflowing me. So it is kind of tempting us to overflow it. To see what we need to do to actually overflow it, let's investigate the source code, which for this binary is the overflowme.s file. The source code for this level is provided in assembly. However, this program actually started out as a C program that was compiled to assembly, and I just made some slight modifications to the assembly to make it a little bit easier to read and understand it for this level 1 challenge. So if we scroll through the source code here of this program, we'll go to the entry point, which is the main function, and then we can take a look at the source code here. So one thing to call out is I'm not actually going to specifically go over in this video what each line of the source code does. However, there are very detailed instructions for almost every single line of assembly. So if you're not sure what any of the instructions or lines do, make sure to check out the source code. So for example, here you'll notice this is the start of the code to actually print the intro message. And we set up here to make a syscall and then perform the syscall, which is what actually prints out this "thanks for not overflowing me." After that, we call a function. We call this echo_print. So for us, let's actually follow this function call and take a look at the code for echo_print, which is just above here. The first thing that happens inside of this function, which is something that happens inside of all assembly functions, is the function prolog. And what this does is it preserves the caller's stack, and it sets up a call stack frame on top of that. So the first thing we do is we actually push the caller's base pointer onto the stack to preserve it. And then we move the stack pointer into the base pointer. So essentially we set the base pointer for the function to be on top of that caller stack. So the base pointer essentially keeps track of the bottom of the stack frame itself. After that, we subtract 512 from the stack pointer. This essentially moves it down 512, which allocates space onto the stack. So recall that the stack grows downwards. This would actually be, if you look at this comment here, this is the equivalent of setting a local variable in C and declaring it as something like char buffer with 512. After we allocate that space on the stack, we then have the code to read the user input and store it onto the stack, which is one of the areas of the program that we are mainly concerned with. So if we take a look, you'll notice here we have a syscall, and ahead of this syscall, we actually have 4 lines that set up all of the registers to make that syscall. So for example, the first one sets RAX to 0 because that is the number for the read syscall. And then more importantly here, we have the RSI register being set with a pointer to that buffer we allocated onto the stack. So that's telling the syscall where we want to store the characters that are received from the keyboard input. And then after that, we move into RDX, the max number of characters that we want to allow to read. So this is done to actually allow developers to prevent buffer overflows by specifying a maximum number of characters that we would receive. And you'll notice that this should actually match the buffer size -1 to prevent an overflow. And in our situation here, this is almost double the space that we've allocated. So because of this mismatch, this program is vulnerable to a buffer overflow, which will actually be a stack overflow since this buffer is on the stack. So in order to both crash this program and exploit it, we'll need to fill up the entire buffer on the stack, which is 512 characters. So there's a couple ways that we could go about and do this. I mean, one is we could just run the program normally and then input this manually, but that would take a long time. Could use a bash script. However, what I prefer to do is actually just to write a quick Python script to output the characters. So I've got one started here called exploit.py. So let's take a look at that. We'll first use this Python script just to generate enough characters to crash the program. And then after that, we'll come back and revisit it later to actually use it as an exploit to jump somewhere in the program we shouldn't have access to. So that's why we have this padding and return address here that we're going to come back and talk about more. For now, we're just going to set them all to be X41, which is a capital A in ASCII. This is the classic character that you use when you're performing your first Stack Overflow. So to run this, we can actually go down here and we can just go Python 3, and it's called exploits.py. And you'll notice it just prints out all of these A's for us. So if we want to, we can actually just pipe the output of this directly into the binary. So if we just go back and recall this, and then we'll pipe it into /overflowme. And you'll notice that we get this, my buffer is open for input. Please don't overflow me. We get all of these A's, which is more than 512. And then we see a segmentation fault core dumped. So generally what a segmentation fault means is that the program itself is trying to access memory that it doesn't have permission to, or the address is invalid itself. To investigate what's happening here further, we'll make use of GDB, which is the GNU debugger. But before we do that, let's actually pass this output into a file because it's a lot easier to pass this input then into the binary inside of GDB if we use a file instead of a Python script. So to do that, let's just call this again, but instead let's direct the output into a file, and I'm just going to call mine AAA. And it's important here not to actually make this a text file or any type of file because we don't want to interrupt the bytes itself. Perfect, and then if we actually just list this out, you'll notice now we have this AAA. Are you looking to up your cybersecurity skills in 2025? The TCM Security Academy has you covered with our affordable and high quality courses. In addition to the 25+ courses, we also offer certifications that feature hands-on labs specifically built to test the skills you need to succeed in cybersecurity jobs. No multiple choice questions guaranteed. Explore certification and career pathways at certifications.tcm-sec.com. Now we can debug this binary with GDB, which will allow us to take a look at the memory and registers while this Stack Overflow is happening. So to do that, we'll just go GDB and then we'll run the binary. So it's ./overflowme. And before we actually run this, we should set some breakpoints so that GDB will halt execution at some key points in this program that we want to take a look at. So to do breakpoints in GDB, you can just go B And then you can either pass in a line number or a label name. So I've created a bunch of labels in the source code actually that makes it easy to see where we're setting the breakpoints. So the first one we'll do is actually this before underscore function call. So then we'll just go before underscore function, and you can actually use tab autocomplete inside of GDB. So we'll do a tab autocomplete there. And then the next one we're going to do is before underscore read syscall. And then we'll do another one that is before function return. Perfect. And now we can actually run this and it will pause at these breakpoints for us. So to run it, we'll go R. However, we do want to pass in the inputs to come from that file we created, which is AAA. Perfect. And now we're running and you'll notice it's done a breakpoint at line 81, which is right here. So the reason I set a breakpoint before we actually call the function is so that we can take a look at the base pointer before we go into that function, and we can also take a look at the return address. So first, let's investigate the base pointer. You can look at registers in GDB using I, R, and then the name of the register, which is RBP. So for me, it is 0x7FFFFFDD70. It might be different for you, but let's take note of this so we can come back to this later. And then next, let's take a look at the return address after we come back from this function, which is going to be on line 82 at return from function. So to take a look at the address of a label, we can go info address and the name of the label, which is going to be return from function. Perfect. And I'm going to take note of it. So mine is all fives and then ending in 51BF. So now that we've got these noted down, we can actually continue on with execution, which to do that in GDB is just C. And now it has broken at line 55 before the read syscall here. So if we go up here into echo underscore print, we can take a look at line 55 and we're just getting ready to set up for this syscall. So before we do that and actually overflow the stack, let's take a look at the contents above the stack right now. So recall, the first thing above the stack is that we've pushed the caller's base pointer. So to take a look at memory in GDB, we use the X command, and then we can pass in some formatters to this. So we'll go /xg. And what this is telling GDB is that we want it to be formatted in hexadecimal. And then the G says to just bring back a quad word, which is 8 bytes. And then we can actually say to look at the memory that's starting at what's inside of the current base pointer. And you'll notice that we get the same one that was preserved before. So this is the memory that's right above the stack. We can then take a look at the memory that is directly above. So if you just hit up and we'll go +8 here. And you'll notice that this is the return address. So the reason for this is because if we actually scroll down to main here, when you call a function, what happens automatically as part of the call instruction is that it actually pushes the return address onto the stack of where the function should return from once it's done. So once this code execution inside of this echo underscore print gets to the end here, and does the return, it needs to know where it's going to go. And to do so, it looks at the stack. So this is what actually makes Stack Overflow so dangerous, is because if we are able to overflow past the base pointer and into the return address, then we can either crash the program or take control of the program ourselves. So to see how this works, let's actually hit C again and we'll continue. And you'll notice we get all of these A's printed out, but at this point we still don't have a segmentation fault. The program is working right now. We're before this function return. So the next thing that happens is what's called the function epilogue here, which actually just basically breaks down or deletes the call stack frame and returns the stack to how it should be for the caller so that their stack is not messed up. And then when we get to this return, it's going to take a look at the address that's on the stack and then jump to it. So if we actually take a look now, if we go x/xg and we take a look at the base pointer, well, you'll notice it's all 4 ones, which are A. And more importantly, if we actually do +8 here, you'll notice that this is also all 4 ones as well. So when we try and return from this function, it's going to try to jump to this memory address, which it does not have access to. It's not able to access, or it's not a valid address. And because of that, the program is going to crash. So if we hit C again here, you'll notice that now we get this segmentation fault and we have crashed, and it's trying to execute what's at this line of memory. So whatever is in blue, that's telling us the line of memory. So it's trying to execute that line of memory, and it's saying it can't because it doesn't have access or it's not a valid address. So for us to complete this challenge, then what we need to do is actually modify our exploit and our input so that instead of putting 4 ones in here, we actually put the address that we want to jump to. So let's hop back to the source code and investigate and take a look at how we could potentially print out, hey, you're not supposed to be here. So let's just do Control F in here, and I'm just going to go, hey, and we see here we have this hidden message, hey, you're not supposed to be here. So let's take a look now if this hidden message is used anywhere. So instead, we'll just search for hidden underscore message. And I'm going to go down here, perfect. And we see here, we have this function called hidden underscore print. So what we can do is set the return address using our exploit and our overflow to instead jump here. So before we modify our exploit, let's actually go ahead and rerun this. So I'm just going to hit run. To rerun this, we don't necessarily need the input at this point, and we'll just hit yes. And now let's take a look at the address of this function. So we'll go info address hidden underscore print, and it is at 55555555129 for me. So if you are following along, keep in mind that yours might be different, so it's going to be important for you to take note of it. So I'm going to copy it here, and we'll copy it in, and then I'm going to exit out of GDB here. With exit, we'll hit yes. And now let's go ahead and modify our exploit. So instead of pushing in all of these 4 ones, now we're actually going to push in this address in the return. So let's go here. I'm going to paste mine in, and we will need to format this slightly to make it be the right formatting for Python to do bytes. So to do that, we'll go /x in front of each of these bytes, which is 2 characters. And then there's actually one other difference we need to make here. So we'll get rid of this 0x, and that is, recall that this is being pushed into the stack from the bottom up. So we actually need to put this backwards for how we would want it to be. So instead of actually being in this order, we'll need to grab this. So we'll go here and basically reverse this. So we're going to put this here, and then this here. Fix this up. Now let's save this, and we can rerun this exploit.py. So we'll go Python 3 exploit.py and just make sure it prints out. And we get all this garbly goop here because these are just the ASCII representations of what it's trying to do for these. We've set our exploit up so that the padding will fill up the buffer on the stack with 512 A's. It will then also overflow the base pointer that's preserved with A's, and then it will push the return address that we want onto the stack where the return address should be. So it's important when you are performing these stack overflows to make sure you get the calculation right for the amount of padding you'll need to set up your return address properly. So let's actually pass this into another file. So we'll go here, and then we'll pass the output of this into, I'm going to call mine jump to hidden. Perfect. And now let's do the exact same thing. So we'll use GDB. We'll go GDB /overflowme. And I'm going to set the same breakpoints here. So we'll go before function call, before read syscall, and before function underscore return. And we'll run it again, but this time we'll pass in that jump to hidden. Perfect. So if you want to, at this point, you can reinvestigate the base pointers and stack. What I'm going to do is I'm actually going to continue And at this point, let's just quickly take a look at the return address. So we'll go x/xg $RBP plus 8. And you'll notice it's still that one ending in 51BF, which is what it should be for normal operation of this function. But now if we hit C to continue and we actually rerun that command, you'll notice now we are going to 5555555129. And if we just quickly double check again, we go info address hidden underscore print here. You'll notice that this actually matches up. So now let's actually hit C to continue. And then we get, hey, you're not supposed to be here, which completes the challenge. So if you were following along, congratulations on getting this Stack Overflow exploit to work. And even though this was a basic one where we are just jumping to somewhere in the program, sometimes that can be enough to still be a major vulnerability to bypass things like password checks or other security checks. However, in the following levels of the Overflowme walkthrough, we'll actually take a look at how we can write our own shellcode and jump to that. But in this lesson, this is where we're going to stop for this exploit itself. Before we wrap up this video though, there's a couple things that I would like to go over. Firstly, you'll notice that we still get a segmentation fault from the program. And the reason for this is because if you actually take a look there, we don't properly call this function. Again, when we set up to call a function, if we look at main, we use the call instruction, and then this is what actually sets up the stack with the return address. But what we've done is essentially we've hijacked the instruction pointer, which is a register in the processor that actually tells it what instruction to execute next. And we've just hijacked this and told it to jump straight to this hidden underscore print function without properly setting up the stack to return from that. So when we actually come down here and go return, it doesn't actually have a proper address to grab, and that's why we get this segmentation fault still. However, we still got our accomplishment done. Also, later on in a subsequent lesson, we'll talk about methods if we don't want to crash the program to be able to fix this as well. So if we just exit out of here, the last thing that I want to talk about is how we could remediate this program to not have a Stack Overflow, and some protections that are built into operating systems to prevent Stack Overflows from happening. So let's clear this away and start by taking a look at the source code for the remediation for this. So the first thing let's quickly look at in the source code is how we could actually remediate the Stack Overflow from happening, which is very straightforward in this one. All we would need to do is either up the amount of space we've allocated on the buffer to be 1 greater than the amount of max characters we've input, or alternatively, we could shrink this down to be 1 less than the amount of characters on the buffer. So these should essentially almost match. We should have -1 on this one, and the reason for that is so that we can have a null terminator at the end of the string. So outside of making sure we don't have stack overflows or buffer overflows inside of our binary, which if we're working in higher level language like C, this could also mean making sure we're using safe functions that prevent stack overflows and buffer overflows from happening. There are also some built-in protections in the operating system to stop them from still being exploited. And I'd like to take a look at 2 of them inside of this level and video, because in following levels of the walkthrough, we'll actually look at how to bypass some of these protections. So the first protection we'll talk about is ASLR, or address space layout randomization. And what this does is the operating system randomizes the memory layout of the binary itself once it gets loaded into memory and run. And essentially this will then put things like the functions, all of the data for the program, and the stack itself into randomized locations, which makes it much harder to exploit this because we don't essentially know where things like the stack or other pieces of code we may want to jump to are. So to just actually see this in practice, let's go ahead and just run the exploit, but outside of GDB. So if we go Python 3 here, and then we'll go exploit.py, and we'll pipe the output of that here into Overflowme. And you'll notice that at this point, we still have this printout here where it has the address in it. However, at this point, we just get a segmentation fault and we don't actually jump to the area in the code where it prints out that hidden message. And that's because it's no longer going to actually be at that same address that we found. When you run this inside of GDB, it actually disables ASLR because it makes debugging a lot easier if your addresses for things aren't jumping all over the place on each execution. However, if you want to temporarily turn off ASLR, just so we can see how it works, you can go sudo and it's sysctl-w for write kernel.randomize_va_space. And we'll set this equal to 0 to turn it off. And now if we actually just go ahead and rerun this, you'll notice that now we get this, hey, you're not supposed to be here, because we have turned off that ASLR. So if you want to turn it back on, you can actually set it to 2. So 2 means ASLR is fully on. And now again, if we just go and run it now, you'll notice we don't get that, hey, you're not supposed to be here. So let's clear this away here and we can talk about the second protection. The next protection we're going to talk about are stack canaries. So to actually learn about how they work, I have written a custom implementation of them in assembly in the overflowme_canary.s source code here. So if we actually just scroll down, I've just added them inside of the echo_print. And you'll notice in the comments here, we have some code here that stores the stack canary onto the stack. So essentially what stack canaries are they are a randomized value that we can get from the operating system to place onto the stack ahead of the caller's base pointer and the return address. So you'll notice here, it's actually located in Linux on the distro that I am at fs:40. So this is a special location to get the stack pointer. And then we actually push this onto the stack. So before we allocate any space or do anything in the program, we push that stack pointer on. And then what this does is if we actually overflow the stack itself, it will overwrite this stack canary with potentially whatever, if it's A's or return address or another part of our exploit. And then what we do actually is if we go down directly to before we're going to return, we actually verify that the stack canary hasn't been tampered with. So for us, we actually grab the stack canary again, so the operating system will keep track for us what it should be, and it will give us back the same one. And then we actually compare it to the one that's on the stack. So it is going to be directly above that base pointer. So we use an exclusive OR and a test. And then we actually jump. So we use a jump to this overflow detected code here where we print out a message and then exit if we detected an overflow. And if we don't detect an overflow, then we just return as usual. So if you're compiling from a higher level language like C or C++, then most of the default compilers will actually just put stack canaries in automatically. However, since we started from assembly, I've gone and written this implementation that is pretty similar to how GCC would handle it. So we can also make this binary as well. So if we go make overflowme_canary, it will build that for us. And then if we run this, you'll notice if we just say hi from Andrew, it runs as it should. However, now if we actually go and pass our exploit into this, pipe this into the one with canaries, you'll notice that we actually get this message where it says, hey, you overflowed me. And it doesn't crash or anything, but it does return an error for us because of how we actually exit the program. But the stack canary catches this and says, hey, you overflowed me. So if you've ever done this in Linux, then you may notice that the actual message that it prints out is usually stack smashing detected, terminated. So I've just added my own implementation here for fun. In following levels of Overflowme, I'm going to demonstrate how you can actually bypass things like stack canaries or ASLR if you're able to chain together multiple vulnerabilities. However, this is going to end this level 1 walkthrough here. Thanks for watching to the end. If you want to learn more about assembly and Stack Overflows, make sure to check out the Assembly 101 course on the TCM Security Academy. I'll drop a link in the description below. Finally, If you enjoyed this video and you want to see more walkthroughs of the Overflowme levels, make sure to let us know in the comments or like this video. Finally, don't forget to subscribe. Thanks for watching.